So I think we can start. And so it's a real pleasure to have here Ashoke Sen, who is going to lecture about superstring perturbation theory. So Ashoke, you can share your screen.
Okay.
Okay. So I think we can start. Thank you.
Okay, thank you very much. So first of all, I'd like to thank the organizers for inviting me to this school. Unfortunately, I couldn't come in person. So the lectures today will be on superstring perturbation theory. Okay. And a somewhat more detailed version of this can be found in my homepage, okay, which I have given here. Okay. And this has, of course, many courses, but you should look for the course on superstring perturbation theory. And there are a set of lecture notes taken by Mrityunjay Verma, which are quite detailed. Okay. And you can also find some concise version of these lectures in this archive paper. Okay. And the relevant sections are sections 2 and 3. Okay. In any case, I'll try to put this up on the web, these lecture notes, so you don't have to copy this. So let me then begin with string theory. So string theory is based on a simple idea, namely that the elementary constituents of matter are one-dimensional objects. Okay, which is what we call strings. And not point particles, which is the usual viewpoint. So this, of course, is a radical idea. But the question that one would ask is why? Why do you want to replace the notion that elementary objects are particles by the notion that elementary objects are strings? So here I'm going to give two reasons. So the first reason is that string theory, and this we will see in some detail, contains gravity. And possibly the standard model of particle physics. Okay. So this part is sure. Okay. Whether it actually contains a standard model, we don't know yet. Okay, so that's the hope. The second reason is that unlike quantum field theories, which are theories of point particles, string theory is free from ultraviolet divergences. So in a sense, this gives a UV finite, unambiguous, this is important, And this is essentially the reason why we study string theory. So the goal of these lectures is to give a glimpse of how string theory works. But in that process, I'll skip many derivations. Okay. However, on the way, I'll also give some exercises. Okay. So the exercises can be done in principle based on the results that we provide. Okay. So when I skip a derivation, okay, then I'll say so. On the other hand, when I leave something as an exercise, that means that that's something that one can in principle work out based on what you have already discussed. And I'll strongly urge you to at least do some of these exercises. The other point I wanted to say at this stage is that please ask questions whenever you have any, okay, instead of waiting till the end, where it's best to clarify the doubts as we proceed. So our starting point will be the action of a relativistic point particle. Okay, and let me write it down, and many of you probably have already seen it. In case you haven't, it doesn't really matter, okay, because I'm not going to use this explicitly. So the action is normally written as integral ds, okay, where this is over some path, okay, and this is the proper time.
I'm just coming. So I'm asking if you the one who organized the hand sanitizer. The hand soap. Okay. Now I bought it. Oh, okay. For you and me. Not for me.
Okay, so this I can write as where x mu, so okay, xi is a parameter that labels the worldsheet or the world line. So this is a parameter. Along the world line. Okay, so if the particle is traveling along this, so xi is some arbitrary parameterization along the world line. Here you can easily see that it's invariant under a change of xi to some function of xi. Okay. And this x mu of xi is the particle coordinate, okay, the physical location of the particle in space and time, okay, as the particle is moving. Okay. And one can show that starting from this action, one can recover the usual dynamics of point particles, of relativistic point particles. Okay. So this is not something I'm going to discuss, but this is we'll write down the action for strings in analogy with this. So as a string moves, it spans a two-dimensional surface because strings are one-dimensional objects. Okay. And one needs two coordinates to label the worldsheet of the string. Okay. So I'll call this xi0 and xi1. Okay, and collectively denote this by xi alpha, with alpha equal to 1 and 2. And then one can write down the action for relativistic string, which is also called the Nambu-Goto action. That alpha is from 1 to 2, goes from 1 to 2, and this symbol is just del del xi alpha. So roughly this can be thought of, this action, just like the word line action was the proper time, this action can be thought of as the area of the world sheet. Okay, and the area is in quotes because it's in really a Lorentzian space time. Okay, it's not the usual Euclidean area, but this would be the Euclidean area, okay, if you are working in Euclidean space. And T is a parameter which is called the string tension. Which is also sometimes labeled as 1 over 2 pi alpha prime. Okay. So alpha prime has the unit, it sets the unit of mass essentially, okay, in string theory. Okay. And for simplicity, we'll set h bar equal to 1, c equal to 1, and alpha prime equal to 1. So these three basically sets the units of mass, length, and time. Okay, so these are the natural units. Okay, at least these are natural units. Alpha prime is a natural, equal to 1 is a natural unit in string theory, but otherwise in a general theory of quantum gravity, one often writes the Planck mass as a natural unit. Okay, but we will use alpha prime equal to 1 as a natural. Now this Nambu-Goto action has this problem that it has a square root, and the actions with square roots are hard to analyze. So we simplify the action by introducing an auxiliary set of variables. Gamma, alpha, beta. Okay. This is sometimes called the world sheet metric. Okay, for reasons that will become clear soon. Okay, but for us, we just think of this as an auxiliary set of variables. Okay, and we write the what is called the Polyakov action, okay, as follows. Okay, I've set alpha prime equal to 1, otherwise there will be an alpha prime here. But this gamma upper alpha beta is just the inverse or matrix inverse of gamma alpha beta. Okay, so this is the same notation that one uses for in general relativity. Okay. Now, if we start with this action and then we eliminate gamma alpha beta by its equation of motion. So gamma alpha beta equation of motion has a solution, okay, where gamma alpha beta is proportional to okay, so this is an exercise. Oops. This is an exercise you can do. Move this. And then if you substitute into SP, we get back the Nambu-Goto action. Okay, this is again something you can check. Okay. So which means that classically the Polyakov action and the Nambu-Goto action are equivalent. Okay. So classically the two actions are equivalent. But we define quantum string theory as the quantization of the Polyakov action. Okay. So we quantize SP. Now, one feature of SP, as you can easily see, is that it has general coordinate invariance, two-dimensional general coordinate invariance. This has nothing to do with the gravity in space-time, okay, which will emerge later, as we'll see. Okay. But this has 2D general coordinate invariance. So you need to gauge fix. So we normally choose what is called a conformal gauge. Okay. So we choose gauge. Gamma alpha beta equal to eta alpha beta. In fact, we do something even simpler. Okay. So we normally weak rotate the world sheet and set gamma alpha beta equal to delta alpha beta. Okay. So in other words, if we think of the xi0, okay, we set xi0 as I tau, okay, where tau is the Euclidean time, Euclidean world sheet time. And as I1, I'll call sigma, okay, and sigma I'll take to be periodic variable. So sigma is identified with sigma plus 2 pi, and that's because we will be working with what is called closed strings, okay, which has no ends. So as it moves, it spans out this two-dimensional surface, which is the cylindrical shape, at least topologically it's a cylindrical shape. So you can think of as tau increasing this way, okay, which is the Euclidean time, and the sigma is this coordinate. Okay. So you'll in fact find it useful to use complex coordinates. So let me introduce all the coordinates that I'll be using right now itself. Okay. So we introduce a complex coordinate. W, which is tau plus I sigma. Okay. And we'll also use another coordinate system Z, which is e to the W. Okay. And this coordinate has this feature that W goes to minus infinity, okay, gives, or maybe I should say, let me write this one more. So this is e to the tau plus I sigma. Okay. So tau goes to minus infinity, gives you Z equal to 0, and tau goes to infinity, gives you Z equal to infinity. Okay. So essentially it maps the cylinder, drop in the W coordinate, it's a cylindrical shaped object. Okay. Z, this coordinate transformation maps it to a plane. Okay. So this maps the cylinder to a plane. Okay. And in fact, I mean, it's also useful to think of the plane as a sphere. Okay. So we add z equal to infinity point to the complex plane. And call this a sphere. So this gives a sphere. Okay. So the z plane will often referred to as a sphere, okay, because you can think of the z equal to infinity point as just a single point. Okay. And that is possible because we'll see that there will be a certain fall-off condition as z goes to infinity. Okay, so that the fields approach the same value in whichever direction you go. Okay, that's the reason why the z equal to infinity. It's useful to think of this as a single point. Okay. But for now, we'll be working with the W coordinate system. Okay, but it's useful to keep this in mind that we eventually will switch to Z coordinate system because it's much easier to use. And I should also say that in this coordinate system, tau ordering, okay, tau ordering as like time ordering. So tau ordering, okay, corresponds to mod Z ordering, because if tau is larger than tau prime, then mod Z is larger than mod Z prime. Okay, by this relation that we wrote down, and this is often called a radial ordering. So when we define the various Green's functions, okay, we'll use time ordered product of operators in the W coordinate system, and those will translate to the radial ordered product of operators in the Z coordinate system. Okay, but again, we'll see this as we proceed. For now, we'll proceed with W coordinate system. Okay, so now I'm going to write down the gauge fixed action. Okay, this is not something that I'm going to derive. Okay, but I'll just state. So gauge fixed action has the following form. Okay. And in this formula, I have not been very careful in writing, in getting correctly the normalization factors and the signs. Okay, because I'm not going to use the action very much. Okay. So this is up to normalizations and signs. This you should just keep in mind. Okay, so let me explain the notation. So this stands for the partial derivative with respect to W. Okay, this is derivative with respect to W bar. Okay. X I have already introduced. Okay, these are the space-time coordinates as a function of tau and sigma, because this surface is embedded in space-time. Okay. These are new fields. Okay, so B, C, B bar, C bar are ghosts that come from the gauge fixing. Okay, and as ghosts, they are all anti-commuting objects. Now, if you look at the equation of motion from this action, the X equation takes the form del bar X mu equal to 0. Okay. And then B bar, C bar, you can easily check that you have del bar C equal to 0, del bar B equal to 0, del C bar is 0, and del B bar is 0. Okay. So this means that these are holomorphic objects. And these are anti-holomorphic. Now, because we have periodic, the sigma direction is periodic. Okay, we can carry out a Fourier expansion. So instead of using these variables, we can work in terms of the Fourier transform, Fourier expansion coefficients. Okay. So let me write down the mode expansion of the various fields. Okay, these are mode expansions consistent to the equations of motion and the various periodicity requirement. So we can write x mu. This normalization is just up to us. There's a minus sign here. These are not equal to 0. Okay, so these are some variables which are rendered constant by the equations of motion. And then B is sum over n, Bn e to the minus nw. C is and notice that the expansion is in linear combinations of e to the nw because of the sigma periodicity. Because e to the nw contains e to the I n sigma, which is manifestly periodic under sigma goes to sigma plus 2. Now, from the action, we can work out the conjugate momenta and calculate the equal time commutator or equal time anti-commutator, depending on whether you are using the Grassmann or the Grassmann even variables. Okay. And this I'll leave as an exercise. Okay, this exercise is up to fixing the constants and the signs in this in front of this various terms. Okay, I don't claim that this has a correct sign, but the commutators that I'm going to write down has the correct sign and normalization. So exercise alpha mu n alpha, this is m alpha mu n is m this is commutator, this is anti-commutator, this is delta. Okay. And similarly for the anti-holomorphic ones, identical. Okay, we just replace this by bars, these by bars, and then you also have x mu p nu. This is commutator. This is the usual I eta mu. Okay, we are going to make use of these commutators a little later.
Excuse me.
Yes.
Why we write the ghost field as anti-commutator?
Because the ghosts are, these are Fourier-Popov ghosts, right? So when you gauge fix, you always get anti-commuting ghosts.
Okay.
Right? It's the usual Fourier-Popov ghosts that you get in a quantization of normal gauge field.
Okay, thanks.
Right? That's why you have anti-commutator ghosts. The ghost fields are anti-commuting. They are Grassmann odd objects. Any other question? Okay. Now it turns out that the action itself doesn't contain the full information about the theory. We need a little more. Okay. And what we need a little more, okay, is the response of the theory of the theory to deformations of gamma alpha beta. Okay. See, the gauge fixing has said gamma alpha beta equal to eta alpha beta. Okay. But we can ask that what happens if we change gamma alpha beta a little bit? How does the action change? And this is necessary because we eventually want to impose the condition that the variation of the action with respect to gamma alpha beta is 0. That's part of the equation of motion. Okay. And that information is contained in this response of the theory to deformations of gamma alpha beta. Okay. So this is captured in the energy momentum tensor. Captured in the energy momentum tensor. Tensor T alpha beta. Okay. So we, in order to complete the information about the theory, we have to now specify what T alpha beta is in terms of the various fields, the elementary fields that we have introduced. Okay. So here again, I'm not going to derive this, but I'll give the result. Yeah, and I'll give the result in this complex coordinate system. So result is that TWW, okay, which by definition is what we'll call T, okay, is given by minus eta mu nu T W bar W bar, which is T bar, okay, is minus eta mu nu and TWW bar is 0. So this being 0, okay, is the condition that this means that the T is traceless, because trace of T, in fact, you can verify in this coordinate system is TWW bar. Okay, and this means that the theory is that you have a conformal invariant theory. Okay, and this conformal invariance will be very important in what we discuss next. Okay. So let's check the conservation law. Okay. So conservation law is del alpha T alpha beta equal to 0. Okay. But in this WW bar coordinate system, this takes the following form. Okay. Del W bar TWW plus del W T W bar W equal to 0. So this is one of the, this is a beta equal to W component. And then the other one is del W T W bar W bar. Okay. So let's see how this works. Okay. T W bar W is 0. Okay, so this term is identically 0. Okay. And this one, this TWW, if you look at the expression for TWW, okay, you see this is holomorphic. Okay. And as a result, del W bar TWW vanishes. Okay, so that's the way the conservation law works. Similarly here, okay, this one is anti-holomorphic, so this is 0, and TWW bar of course is 0. Okay, so indeed the conservation law of energy momentum tensor is satisfied. Okay. But in fact, we can construct not just one conserved charge, but an infinite set of conserved charges, as we'll discuss soon. Okay, now let me discuss some general aspects. Okay, we'll come back to T conservation law in a few minutes. So let's just discuss some general aspects. So suppose that Kw is a holomorphic field, any holomorphic field. Then we have the equation that del W bar Fw Kw equal to 0, where this is any holomorphic function. So this one can be written in the following way. I'll just write this as del W bar Jw plus del W Jw bar equal to 0, where Jw bar by definition is 0. And this one is 0, because this is okay. So Jw, okay, let me define this. Jw is Fw Kw. So because this is holomorphic, okay, K is a holomorphic operator, F is a holomorphic function, del W bar Jw is identical as 0. This is 0 because by definition Jw bar I'm taking to be 0. Okay. And so this gives a conserved current. Okay. So this in turn means that you have a conserved charge. This means that Q tau, okay, which if I write this as integral real W equal to tau, okay, that's the condition that you are only doing this integral at a fixed time, okay, of Jw dw. Then you can easily convince yourself that using these relations, that Jw is given by that Jw bar is identical to 0, that this can be made shown to be proportional to integral J tau d sigma. Okay. And this is of course conserved charge, right? Because that when you have an equation like del alpha J alpha equal to 0, so this is conserved since del alpha J alpha equal to 0. Okay. Which means that Q tau is tau independent. Okay. So this means that Q tau, which is integral is tau independent. Okay. Now we'll choose the normalization of Q in such a way that this integral contains 1 over 2 pi I factor. Okay, this is just a matter of convention because overall normalization doesn't affect the conservation law of charge. Okay, and we'll see why this is useful. Now suppose phi W bar is another operator, not holomorphic necessarily. And let's suppose that we are trying to compute Q with phi W bar. Okay. I have dropped the index tau from here, okay, because Q is the tau time independent. Okay, but let's suppose that we are trying to compute this. Okay. So this I'm going to write as Q tau plus. I'll explain what tau plus is, times phi W bar minus phi W bar. Okay, let me put a W0 here. Okay, because I'm going to use W for something. Okay. So tau plus is chosen to be larger than real W, and tau minus is chosen to be smaller than real W. see that I have done this. Yeah, okay, correctly. Okay. And this we can do because Q is tau independent. Okay. But once you have written it this way, okay, we can write this commutator in the following way. Okay. That we can write this as integral real W equal to tau plus of time ordered product of JW of W phi of W0 bar minus integral real W equal to tau minus time ordered product of JW of W phi of W0 bar. Okay. So you see the point is that this time ordering automatically puts JW to the left in this integral because tau plus has been chosen to be larger than, so this is W0. Because tau plus has been taken to be larger than real W0, whereas here it automatically puts JW to the right of phi W0 bar because tau minus has been chosen to be smaller than W0, real W0. Okay, so this is exactly this difference. Now on the cylinder, what this means is the following. That you imagine that you have this point W0 here, and you have two contours. Okay, so tau increases this way. So you have two contours. This is that tau plus, this is that tau minus. Okay. And we have the difference, the same integrand, okay, time ordered product of JW phi, okay, except that in one case it's integrated along this contour, in the other case it's integrated along this contour. Okay. And of course tau plus and tau minus can be taken to be anything, so you can bring them close, okay, being on two sides of W0, okay, and essentially collapse them onto each other. Okay. So this you can essentially deform, okay, into a cylinder. This is W0, and the contour basically can be made into a contour around W0. Okay, it of course cannot cross W0, okay, but it can be made into a contour around W0. Okay. So this is what I'm going to write in the next slide. So what we learn is that Q with phi W0 bar is essentially a contour integral around W0, okay, of the time ordered product of JW of W of phi W0 bar. Okay. But this contour will of course just pick up the residue at W equal to W0. Okay. So this means that the coefficient of 1 over W minus W0 in the product gives the commutator. We can in fact also have the converse, that we can, given a commutator, so converse is that given a commutator, we can determine singular terms in the operator product. Which basically means that all the various commutators that we had seen earlier, we can now turn them into information about operator products. So I'm going to write down certain results, and I'll leave this as an exercise for you to check this. So exercise, okay, this can be derived based on what we have already discussed. That BW1 CW2 is 1 over W1 minus W2. So this symbol basically means that we are not talking about the non-singular pieces. This only captures the singular pieces. Okay. So this will come from the BC anti-commutator. Okay. I should have said that this is here in this analysis. I have assumed that these are commutators. Okay. Because I have taken Q and phi to be Grassmann even. Okay. But even if they are Grassmann odd, these become anti-commutators. Okay, and that has to do with the fact that in the definition of the time ordering itself, okay, if both are Grassmann odd, okay, then time ordering includes a relative sign flip between the two orders. Okay, so that's why for the anti-commuting objects or the Grassmann odd objects, also it automatically picks up the anti-commutator. Okay. So this is given by 1 over W1 minus W2. Sorry, I'm still in the W coordinate system. And I should just say convention that I have implicitly used here, they're all products are inside time ordering. The other point I want to mention here, whose significance will become clear only later, okay, is that the singularities in the operator product are the same in all coordinates. Okay, because they are local properties. So even if you are using the Z coordinate instead of W coordinate, they will be the same. Okay, because we are going to use these also in the Z coordinate system, which again, we have not really said very much about it except introducing it. Okay, but we'll see later how to transfer the results from W coordinates to Z coordinates. Now let me come back to this statement of conformal invariance. So I already said earlier that PWW bar equal to 0 means that the theory is conformally invariant. So a conformal transformation essentially is any locally holomorphic coordinate transformation. So W goes to some function of W. This is locally holomorphic, okay, which means that it may have poles and branch cuts outside certain domain. Okay, but we can work locally at least initially. So the various fields, and this is a symmetry of the theory in a sense that I will be describing as we go along. Okay. But let me introduce some definition first. Okay. So a field phi W bar is a primary of dimension. Okay. Sometimes one also refers to dimension as weight. So I'll be using this interchangeably. Sometimes I'll refer to them as weights, sometimes dimensions. So the primary of dimension h bar h if it transforms in the following way. Okay. So the coordinate in if phi w denotes the field phi in the w coordinate system as described in the w coordinate system. Okay. And if this is given by f prime of w to the h, f prime bar of w bar to the power h bar, phi of fw bar, fw bar. Okay. Now these are arguments, okay, and this subscript, okay, basically tells us in which coordinate system you are measuring your field phi. Okay. So this subscript, okay, so phi of fw means that phi is measured in fw coordinate system. Okay. And this relates the phi measured in w coordinate system to phi measured in the fw coordinate system, right? That's the conformal transformation. Now this is the correct way of writing things, okay, but it's somewhat cumbersome. Okay. So the convention that I'll be using, okay, is that I'll basically drop this subscript fw, okay, because this subscript fw is also in the argument. Okay. So whatever be the argument of phi, we, unless stated otherwise, we think of phi being measured in that coordinate system. Okay. So just to give an example, if I refer to as phi of w, okay, this actually means phi measured in w coordinate system. Okay. On the other hand, if I write phi of z, okay, this should be interpreted as phi measured in the z coordinate system. Okay. So phi of z is not simply that you replace w by z in the argument. Okay, you have to also change the coordinate system, right? That's the notation we are going to use. Okay, but if you find this confusing, okay, it's you can always write this as a subscript, that which coordinate system we are measuring the field. Are there questions so far? Okay, so now let me talk about infinitesimal conformal transformation. W, let's clean the W coordinate system. W goes to W plus epsilon W, okay, where epsilon is a small, is a function of W with small coefficients. This is generated by Okay. So remember that this was a conserved current, right? Because we assume we declare that this is the W component and then the W bar component of the current is 0. So this was a conserved current. And so the corresponding transformation that it generates is W goes to W plus epsilon W. Okay, and this essentially generates the W bar goes to W bar. Let me write this also here. W bar goes to W bar plus epsilon bar W bar. Okay. And although for physical transformation, epsilon bar, of course, is complex conjugate of epsilon, but often it's useful to think of epsilon and epsilon bar as independent transformation. Okay, so this part of the coordinate conformal transformation is generated by this part, and this is generated by this part. Okay, because individually they are conserved.
And here epsilon is holomorphic, right?
Epsilon is holomorphic, yes, indeed. And this is anti-holomorphic. Yes. Because this was holomorphic, right? Look. Here, this was holomorphic and hence epsilon is holomorphic. Okay, now exercise. Okay, let me give a little more hint maybe. So this means that if we take this operator product, okay, this means that the epsilon W, PW, phi W0, W0 bar, okay, this, the singularities in this operator product knows about the commutator with phi W0 bar. Okay. But this, of course, is this conformal transformation by definition, right? This is a conformal transformation of phi because the commutator with a generator is the transformation itself. And that we can read out because we have already specified what the transformation law of phi is. Okay, here you have to, of course, take f to be W plus epsilon W. Okay. So using that, okay, you can determine the operator product. So I'll leave this as an exercise. The T of W, phi of W prime bar is H over W square again, all these are up to finite terms. And T bar is similar. T bar of W bar okay, now exercise. Okay, again, something that you can already do based on what I have given. TW BW prime is 2 over W minus W prime square BW prime plus 1 over W minus W prime del W prime BW prime. Okay, how do you determine this? Because I have already given the T, remember, you had this formula of, I think, minus, I don't remember exactly what was the formula, maybe plus C del B, something like this. Okay, you can read this out, and I have given the BCOP, the operator product expansion. Okay, so using this, we can derive this. Okay. And this means that B is a primary of weight 0, 2. And similarly, you can determine the conformal weights of other conformal transformations of the other fields that you have introduced. So let me describe that. So exercise. That all of these are primaries. C is a primary of weight 0, -1. Then B bar is a primary of weight 2, 0. C bar is a primary of weight -1, 0. This, for example, is a primary of weight 0, 1, and del bar x mu is a primary of weight 1, 0. Okay, and you can go on for various other operators.
This is H, H bar, correct?
H bar, H.
Oh, H bar, H, okay.
Yeah, the H bar, H, because maybe it's a somewhat unusual notation, but the reason for writing this way is that normally one thinks of the anti-holomorphic ones as left movers and the holomorphic ones as right movers. So left mover dimension I'm writing on the left and right mover dimension on the right. Okay, this is the convention that I'll be following all through. Okay, so using this convention, using this results, we can convert the mode expansions to Z coordinate, from the W to Z coordinate. Okay, remember Z was e to the W. Okay, so here I'll leave as an exercise that we had B of W as sum over n Bn e to the minus nw. Okay. This tells us that B of Z is sum over n Bn Z to the minus n minus 2. Okay. Now notice that Bz means it's Bz of Z. Okay, because it's not that B, the same B. Okay, you have transformed it from the W to Z coordinate system. Okay, so that gives some additional powers of Z. That's why this minus 2. Okay. Similarly, C of Z will be sum over n Cn Z to the power minus n plus 1. Okay. B bar of Z bar will be sum over n B bar n Z bar to the power minus n minus 2. And this C bar of Z bar will be sum over n C bar n Z bar to the minus n plus 1. Okay, so these all you can verify explicitly, because once you have the conformal weights, we can convert these from W to Z coordinate system. Now, I should say that not all operators are primaries. Okay, the very fact that I have defined primary operators means that clearly not all operators should be primaries. So exercise, if phi is a primary of dimension h bar h, then derivative of phi is not a primary. Okay, from the transformation law of phi, you can find out the transformation of the derivative of phi, and you can easily convince yourself that it's not a primary. Now, even for non-primaries, we can assign conformal weights or conformal dimensions. And the way it goes as follows, that if an operator transforms as a primary of weight h bar h under W goes to lambda times W, then its weight is h bar h. Okay. In other words, not all operators will transform as primary under an arbitrary conformal transformation. Okay. But the operators can be classified so that they at least transform as like the way a primary will transform under this limited class of conformal transformations, which is just scaling. Okay. W goes to lambda times W. Okay. And so if it transforms as weight h bar h under this limited class of transformations, then you call that the operator has weight h bar h. Okay. So here I'll give a small exercise, okay, that if phi is a primary of weight h bar h, then this has weight h bar h plus 1. Okay, so this is something that you can check explicitly.
Sorry, Ashoke, do you hear me?
Yes, I do.
Is it W going to lambda W or Z going to lambda Z?
Okay, it doesn't really matter because I mean, I have defined it locally, right? At this stage.
Okay, I see, okay.
Yeah, meaning the transformation that I described, right? I mean, which coordinate system I use doesn't really matter at this stage.
Okay.
Yeah, so if you use global transformation, indeed is Z goes to lambda Z, but at this level, it doesn't really matter because it's just local fields.
Okay, thanks.
Okay, any other question? Okay. Now, of course, you can say that this doesn't make sense globally because W, the real W has a period 2 pi, right? You can't just scale it up. But this is, again, we should think of this as a local transformation. That in a local coordinate patch, if it scales like this, then inside that local coordinate patch, phi transforms in that way. Okay, some more exercise. TW1, TW2 product. Okay. This you calculate, use expressions in terms of BCX. Use expression in terms of BCX. Okay, and then use the product of B with C and X with X and so on. So this is given by D minus 26 over 2 W1 minus W2 to the 4 plus 2 over W1 minus W2 squared TW2 plus 1 over W1 minus W2 del W2 TW2. Okay. Where what is D? Okay. D is the number of values taken by the index mu. Okay. So this is the space-time dimension. Okay. So in this product, the D basically comes from the D part, D comes from Tx. This part of the energy momentum tensor, which is minus eta mu nu okay. And the minus 26, this comes from the BC part. Okay, but this is the final result. Okay. And similarly for T bar. Okay. Similar for T bar product. Okay, again you have a D minus 26. Okay. So this tells us that for D equal to 26, okay, T is a primary of weight 0.2. Okay. And similarly, T bar will have weight 2.0. Okay. So T bar has weight 2.0. Okay. So it's not quite apparent at this stage. Okay, but let me just say it at this stage itself that we will see that D equal to 26 is necessary for consistency of the theory. Okay, so from now on we will set D equal to 26. So D equal to 26 is needed for consistency. So we work with D equal to 26 from now on. Okay. And we'll see later how to connect this to our 4-dimensional space-time. Okay, because that's where we live. Okay, so we have to understand if string theory has anything to do with nature, we have to understand how we can reconcile this D equal to 26 with D equal to 4. And this is something I'll discuss briefly later.
In 2 dimensions, the stress tensor is a descendant of the vacuum. So why do we need it to be a primary?
Well, as I said, in this case, we don't need it. I mean, it's not apparent, right? But we'll later on, when we introduce the BRST chart, you will see that it's necessary for the importance of the BRST chart. Okay? And that is needed for the consistency of the theory.
I see. Okay.
Of string theory, not for the consistency of conformal field theory. Okay? But when we are trying to actually formulate a string theory, right? And we'll see that string theory is more restrictive than just conformal field theories.
I see. Thank you.
If you are just doing conformal field theory, you could live with D not equal to 26. Okay. I should also say that this D minus 26 is known as a central charge. Okay. This is a convention I'll be using. Okay. So when D is not equal to 26, this has a name, it's called central charge. And in a CFT, it's perfectly allowed to have a non-zero central charge. Okay, it's only in string theory that we have to demand that the central charge is 0. Okay, so given that P is a primary of dimension 2, 0, okay, we can now convert the expansion, okay, from the W coordinate to Z coordinate. So if we expand in the W coordinate as ln e to the minus nw, okay, this becomes in the Z coordinate as ln z to the minus n minus 2. Similarly, T bar of Z bar as ln bar Z bar to the minus n minus 2. Okay. So from now on, we work in Z coordinate system. But the Hilbert space interpretation will still be on the cylinder. That's the W coordinate system, which means that the time ordering will always be will be with respect to the time in the W coordinate system. Okay. So in Z coordinate system, it will become radial ordering, okay, and so on, right? So when you talk about the states, right, a state at a given time, okay, if you are using, for example, the Schrodinger picture, you want to specify the state at a given time, it will be at a fixed t. Okay, that's the way we'll think of quantum states. Okay, now some definitions. We'll define the vacuum. Okay. Now the vacuum is not necessarily the lowest energy state, okay, but we'll define the vacuum in the following way. This is a spatial state such that phi z z bar acting on vacuum is finite for any finites and any local operator phi. Okay. And this has put strong restriction on this vacuum, as we'll just see. Okay. So example, okay, let's take B of Z on the vacuum. Okay. Now the B of Z has an expansion of the form sum over n Bn Z to the minus n minus 2 on the vacuum. Okay. So if you want this to be finite at Z equal to 0, this will mean that Bn acting on vacuum must be 0 for n greater than or equal to minus 1. Similarly, you can easily verify it. B bar n on vacuum should be 0 for n greater than or equal to minus 1. Okay. And Cn C bar n acting on vacuum should be equal to 0 for n greater than or equal to 2. Okay, it just follows from the mode expansion. Okay. You can also check that alpha mu n, alpha bar mu n, the vacuum equal to 0 for n greater than or equal to 1. Okay. And this p mu on the vacuum should be 0 for, well, p mu is acting on the vacuum is just 0. Okay. Because this follows from the fact that if you remember in the expansion of x mu, we had this I p mu tau. Okay. And z equal to 0 is tau goes to minus infinity, right? So in order that this remains finite, we have to have p mu acting on the vacuum equal to 0. So I'll leave also as an exercise. ln bar on the vacuum equal to 0 for n greater than or equal to minus 1. Okay. Now, of course, this one follows trivially from mode expansion of t bar, but also, okay, somewhat non-trivially by expressing tt bar in terms of the basic fields x mu b c b bar c bar, and then using the mode expansions of these basic fields. So you can try both ways. Okay, this is a little more complicated because you have to use the expression for t in terms of those fields, and then expand each field in its mode expansion, and then check that by using these relations, okay, that indeed these results hold. Okay, that ln bar acting on the vacuum gives you 0 for n greater than or equal to minus 1. Now I'm going to introduce another property of, again, of a general CFT, okay, which is called the state operator correspondence. Okay, this I'll state without proof. And you may learn more about this in the parallel conformal field theory course. And so this says that for every local operator, v z bar, there is a state v, which is obtained as v of 0 acting on the vacuum, and vice versa. Now, given any local operator, right, of course, you can define a state by this procedure, right? Because by definition, this should be a finite quantity. Okay. What is somewhat non-trivial is the opposite, that every state can be written in this way. That given any state, we can find a unique local operator such that it can be written in this way. Okay, but this is a property of the conformal field theory which one can prove with some effort. I'll just give some example. That C of Z, okay, if this is the operator, the corresponding state is C on the vacuum. This is V need not be primary. Okay? V can be non-primary. So let's take a non-primary del C of Z. Okay? The corresponding operator, corresponding state is C0 on vacuum. Then del x mu of Z, the corresponding state is I by root 2 alpha mu minus 1 on the vacuum, etc. Okay, and you can check that these are all non-zero, okay, by the property of the vacuum that we have obtained earlier, right? I mean, these are all compatible with this. Okay, so C on vacuum, for example, is not zero, even though it's positively moded, because this is a relation it satisfies. Okay, exercise e to the I k dot x. Okay, this is a strange operator. Okay, it's a composite operator. It's in fact has to be defined by appropriate normal ordering prescription. Okay. This is a primary of weight k square by 4, k square by 4. Okay. And the way you check this is to compute operator product expansion with T of Z. Okay. So T of Z, remember, has this structure minus eta mu nu del x mu del x nu. Okay. And we have this OP, okay, which I didn't write down, but it can be easily derived from what I have written down, that this times x nu of W, okay, is minus 1/2 Z minus W eta mu nu. Okay, I had written on the OP of the derivative of x mu is derivative of x nu. Right? This is obtained by integrating that. That had a minus 1/2 Z minus W square. Okay. So from that you can figure out that this OP is given by minus 1/2 Z minus W. So you take this expression for T, okay, and calculate the OP with e to the I k dot x. You bring down this factor twice, because you have to first take the OP of this with e to the I k dot x, and then of this with e to the I k dot x. And you can check by doing that it becomes a primary of the weight k square by 4, k square by 4. Okay. This 1/4 comes because you get minus half square. Okay. And we will define the state k as e to the I k dot x of 0 in the vacuum. Okay, and this after appropriate normal ordering, we can show that this is nothing but e to the I k dot x. That small x appeared in the expansion of capital X. Okay, minus I k dot small x acting on vacuum. Okay, so this is the usual momentum carrying states. Okay, so k has the interpretation of space-time momentum. Okay. So in the CFT, the complete basis of states is obtained from the various oscillators Bn, Cn, alpha mu n, B bar n. Okay, for appropriate range of n, of course, because many of them annihilate the vacuum acting on k. Okay, so these, of course, commute to this e to the I k dot small x, right? So whether they are 0 or non-zero on the vacuum is determined by on this state is determined by whether 0 or non-zero on the vacuum. Okay. So you can build a whole basis of states this way. Okay. And the corresponding statement for operators is that the complete basis of operators, because of the state operator correspondence, for every basis state there must be an operator. Operators is obtained from products of derivatives of BC and by working hard, you can establish which basis state corresponds to which operator and so on. Okay, in this, but we will not need to do this very explicitly because we only need this for a few low-lying states. Okay, in the explicit examples that we'll be doing, we'll only need it for the few low-lying states. But in principle, you can build this whole infinite tower of basis states in the CFT, and you can find the corresponding operators by taking products of these known basic operators, basic fields. Yeah, I think I have about 15 minutes.
Yes, yes, you have 15 minutes more or less. Yes.
Okay, thank you. Okay, now some more definition. For any operator V, any local operator, we define as the conformal transform okay, so it's basically the operator eating in the new coordinate system. Okay, this position. So example, if V is primary of weight h bar h, then f dot V of Z is f prime of Z to be h. Okay, if it's not primary, then in general, the transformation is more complicated. We also define I of Z as a conformal map as -1 over Z. Now we define a brass state, okay, again a spatial state, such that is finite for all finite points Z and all local operators V. Okay. It's similar to the way we defined our vacuum, our gate vacuum, okay, except that here we are acting on the left and we have transformed by this inversion map. Okay, I goes to Z goes to -1 over Z. So we first transform V by this inversion map, okay, and then act it on the vacuum on the left. So just as an example of how these constraints work, that if you take So this in turn implies that similarly, okay, these I'll leave all as an exercise. So this now leads us to the definition of the BPZ conjugate state. So given a state V equal to V of 0 on the vacuum, we define BPZ conjugate state V as okay, we just transform V and then find the BPZ conjugate state. Okay, so just to, if you are if you want to be familiar, get familiarized with this, I'll give an example. So find the BPZ conjugate of the C1 on the vacuum and C0 on the vacuum. Okay, which states are the BPZ conjugates to this? So exercise. Zero, ln equal to 0. I like to say ln and ln put together. Okay, now definition of correlation function. So we'll define the correlation function as a vacuum expectation value. Okay, vacuum is this particular state, and the radial order product okay, so the radial ordering is basically mod Z order. Okay, you have to order these in the order of increasing mod Z values from right to left. Now, from this relation and the earlier relation about the conjugate vacuum, okay, we see that this is true, that this vacuum is annulled by L plus minus 1 and L0. This is also annulled by L plus minus 1 and L0, and also for L bar. Similarly, for L bar plus minus 1. Okay. So this means that we have a relation that if you have L plus minus 1, 0, act with the taking the commutator of this is 0, because L plus minus 1 annihilates the vacuum on the left as well as on the right. Okay, so this commutator is 0. And physically, these, if you take L plus minus 1 and L0, okay, generate infinitesimal conformal transformation Z goes to Z plus epsilon minus 1 plus epsilon 0 Z plus epsilon 1 Z square. Okay. And similarly for the Z bars. Okay. So this means that this correlation function is invariant under this conformal transformation. Okay. And let me write down the finite version of this transformation, and then maybe I'll end. Okay, so this is not an easy exercise, but one can in principle check, okay, that the finite version of this transformation is Z goes to AZ plus B over CZ plus D, where A, B, C, D are complex. Okay. And overall scaling of A, B, C, D doesn't do anything. Okay, so you can put the condition that AD minus BC equal to 1. Okay. This is known as the SL2C transformation. So let me write this again. So this transformation, what it does is it maps the complex plane plus the point at infinity to complex plane plus infinity in a one-to-one fashion. And this is in fact the maximal transformation, maximal possible transformation of this kind. With this property. Okay. And so because of this, okay, that this is a conformal transformation, okay, and of course conformal, the theory has conformal invariance, okay, plus it maps the complex plane plus infinity, which, as I said, we'll just call a sphere. It maps the sphere to a sphere in a one-to-one fashion. Okay, it's an invertible map, and so that's the reason. That's the reason why this is a symmetry of the correlation function. Okay. And this probably you will learn more in your conformal field theory course. Okay, but I just thought I'll introduce it now itself because we'll be needing this in the later lectures. Okay, so I think my time is up. Is that right?
Yes, in principle, yes. So we have some times for questions, either from the audience here or from people following the lectures online. Yes, okay. We have a question here.
So how do you do the quantization if your topology is not a cylinder, if you have a higher genus topology? Is it just local?
No, we'll define later, maybe not next lecture or the lecture after, how to systematically construct the higher genus correlation functions. Okay. And we will see that we will not try to find the correlation function as vacuum expression value of anything, okay, but by gluing the spheres. So we'll not try to formulate a Hilbert space interpretation of the higher genus correlation functions. And that will not be necessary for studying string theory. So the Hilbert space interpretation, in fact, works only for the cylinder and maybe in some limited sense on torus, but not on higher genus surfaces. Does that answer?
It's okay. Okay. If there are other questions, even from people online. So otherwise, at 3 p.m., which means for you, Ashoke, you have to do the conversion. What time will be?
7:30. I think it's 7:30 p.m.
Yes, we will have some time for extra questions. So